Welcome to yet another video of the BRICS Astronomy Research YouTube series, the place where we dive deep into research that researchers across the BRICS countries are currently embarking on. I'm your host, Muleboholo Kulwane, and I'm pleased to have you with us today. On today's episode, we have something truly special for you, and I know you'd enjoy. We have a researcher from one of the BRICS countries that form part of the BRICS Intelligent Telescope and Data Network. If you have never heard about this, please go on to our webpage, which is www.bricsastronomy.org, and find out more about this initiative. Our guest today will briefly highlight their expertise and achievement. Without any further ado, let's jump right into it. We have, sorry, yeah, sorry. So we also have Narusha with us here, and Narusha. Oh well, she'd give introduction. Maybe. Let me first start by introducing myself since we didn't formally meet, right? So my name is Muleboholo Kulwane, right, and I'm based at the South African Astronomical Observatory, right, and
Mhm.
really working on BRICS astronomy, right? So South Africa holds the BRICS astronomy secretariat, which lies with the Department of Science and Innovation. So I'm working on the BRICS project, and I'm working with Duduzile Kubeka. I think maybe you could have interacted with her while she was in Brazil, I think last year or the year before that. I don't remember which. I think, yeah, 2023, right? And
Mhm.
yeah, so we are also joined by Narusha. And Narusha, you please feel free to introduce yourself.
Hi, so I'm Narusha
Hello.
Isaacs. I recently joined the BRICS team as well as the IDEA team as a data analyst. So I'm just getting started, but I am actually a PhD candidate in astronomy. So I have a bit more astronomy background, um, bringing that part into the BRICS, um, yeah, into the BRICS sector.
No, perfect. So I think, yeah, Dr. Eder, do you want to give like just a brief introduction in terms of who you are and who you work with in Brazil?
Yeah, sure. Well, I'm an astronomer. I study physics, and then I follow the normal career path of students that goes to the academic research.
Yeah.
I did my master's and doctor here in Brazil, and I worked at some point. I went to work as a resident astronomer at in Hawaii at CFHD Observatory. That's when I started getting into more instrumentation and working on more observational astronomy. And then I came back to Brazil to for a position at the LNA. That's the National Laboratory for Astrophysics. You guys probably know Bruno Castilho. He is our representative at BRICS Astronomy, and he's also at LNA. So he's my colleague, and since 2013, I've been working on research and instrumental development and other things that we do at LNA. LNA is an important institute in Brazil because that's where we concentrate all of our resources, the optical and near-infrared observatories that Brazil has access to, like Gemini, SOAR, or even OPD, which is our observatory in Brazil. They're all managed and developed by all the partnership is developed by LNA. So I think that's it.
Yeah.
Maybe if you guys have more specific questions, you can ask me, and I'll be pleased to answer.
Yes, most definitely. I think we based on the summary that you gave us, we had prepared a few questions, right? But then I guess we also wanted to give you an opportunity to then present what your research is about, right? And once you're done with the presentation, we can then head into maybe a brief question and answer session, and we can then conclude the interview.
Okay, sure. Yes, it all started when I was still an undergrad, working in an outreach observatory at the university. And I got really interested by a topic that was still burning, which was the research of exoplanets. At that point, we were when was that? It was into the early 2000s. So in those years, we just had a handful of exoplanets detected so far. So it was a science that was growing fast because people were starting to develop instrumentation that were capable of detecting exoplanets. So I got very interested in that topic, but I couldn't find anybody in Brazil that was actually working only on that research topic. So I got to find somebody who was close enough to exoplanet research that I could do my research in exoplanets, but get the experience of those people. And it was mainly people that worked in binary stars, in the optical and near-infrared range. So that's when I started, and I did my master's on reviewing the subject of exoplanets. Then I did my PhD on some specific systems that I studied using multiple techniques. So when we're researching exoplanets, you need to confirm this from several different techniques. It's not enough to just know it exists from one technique, because one technique gives you the orbital period, but the other technique will give you the mass, and the other technique will give you the composition. So you gotta use different telescopes, different methods to observe the same system, to characterize it, and to fully understand what's going on. And so that's mainly what my thesis was about. I was learning more about those techniques at the same time as I was characterizing some specific systems. And I should mention that I worked closely at that time with with a group of research in Texas, in the US, where I spent 1 year during my PhD, and at the University of Texas at Austin. And there they provided me with some access to HST data, which was very important for my thesis, because we're combining radial velocity, which is a technique that measures the velocity of the star to detect the orbit of the planet, but also from the space telescope, the Hubble Space Telescope, we could measure astrometrically the position of the star, the same star, and with the changes in the position, we could constrain the orbit of the star around the center of mass, and therefore to also characterize the planet more thoroughly. So that's basically what I did in my PhD, and then I followed, as I mentioned before, I went to work in Hawaii and the CFHT Observatory, where I spent almost 3 years there learning a lot about instrumentation. So that's where I got a very deep feeling on how complicated, or how instrumentation can be very tricky, and you need to understand the details, because it's not only in the instrument itself, but also the software that controls the instrument, the software that analyzes the data. So I was working more on learning all those things, all the procedures to observe and to collect data, to analyze it, and then to transform it in scientific information that we can do science later. So and yes, so that's basically the research, the combination of the two research topics that I already described, but that's when it comes together, because you learn instrumentation from one side and you learn science from the other side, and you combine these two to make it to learn about the big picture.
Perfect. Perfect. I guess you also answered the question. I guess one of the questions that we wanted to ask was also how did you merge the two fields where your research and instrumentation too, right? I guess that then covers that question, right? And
Okay.
maybe to move on. I think maybe as we move on, I think Narusha and I will have different questions for you, right? And
Okay.
maybe Maybe one question that we can find that we can ask is that how do astronomers actually find exoplanets? And maybe you can explain that in very simple terms that maybe laymen can also understand that. Yeah.
Okay. So there are several, as I mentioned, there are several different methods to detect exoplanets. But one of the most successful method is the one that detects when the planet passes in front of the star. It causes a very tiny decrease in the brightness of the star. And then when it gets out of the passage, the star comes back to this regular brightness. So when this small decrease in brightness, that's when you learn there is a planet there. So there are specialized missions like the Kepler mission, like the TESS mission from NASA. They survey the whole sky to look for these brightness variations in all stars. So when you see some variations that are very particular of a particular shape, tells you that there's an exoplanet there. So that's the first hint you have. There's an exoplanet there from this method. So then after that, of course, you have to follow up with other techniques to learn more about it. Another technique that was the one that detected the first exoplanet around a solar-like star is the radial velocity technique. This is done by spectroscopy. So you basically have to observe the star with an spectrograph, which breaks down the light into several different colors in a simple way of explaining it, but make like a rainbow, of the light of the star. But then that rainbow has sharp lines, and these sharp lines they move around by the Doppler effect when the source that's emitting the light moves back and forth. So that's a way, a direct way of measuring velocity. So we basically is using the spectra of the star to measure its velocity. And then when you measure several spectra during several days or months, you can measure variations of this velocity due to the presence of a planet around that star. So that's a very successful also technique to detect planets. That was the first to detect a planet around a sun-like star, and it already detected thousands of planets as well. So these two techniques are, I think, are the main ones that are used to find planets. But finding is just the first step. Then the next step is to learn more about it, characterize it, and know what's going on that system that you detect.
Perfect. I guess since we're talking about techniques now, have you worked on, or maybe have you detected like, for instance, asteroids that are heading towards Earth, both in time? I know there are recent asteroids that recently or meteorites that recently hit Earth in a couple of places, and mainly around the region of Russia, right? So have you had the pleasure of working on telescopes that have detected such impacts that are heading towards Earth?
This when I'm talking about exoplanets, we're talking about very distant objects. These are planets in stars, around stars. They're very distant from us. But when we talk about objects that are close to us, those are objects in our solar system. So those are like asteroids, comets, planets. Those are orbiting the sun. The sun is the closest star to us. But finding a new planet in the solar system, it requires this planet to be very hidden from us, because we've been studying this place, which this is our environment. This is the closest environment we have in astronomy. So we know it very well. But of course, there are still hidden places. Now, there could be orbits that are hard to detect, or very tiny objects that are hard to detect as well. So of course we can have, but those require different techniques. This is not the same technique. We don't use spectroscopy and you don't use transit. We use usually wide field imaging to detect new asteroids that are coming towards us. This is basically this is the main technique used.
No, perfect. Maybe just to refine the question, I guess with the research that you've just sent now, and maybe looking at the papers that you have published, I think your research has led to the discovery of unique planetary systems, right? And then maybe my question would be what's the most exciting exoplanet that you have found, and why is it special?
Okay, I think the one every system is special on its own because they all have specific characteristics that are particular to that system that are interesting in some way. Yeah. But I can say that the most cited paper I have is from the system called EUMIC, which is a very interesting one. And what makes it interesting is because this is a very close star, an M-dwarf star. M-dwarf star is a very cool star. It's much cooler than the sun. The sun has a temperature of about 5,800 degrees, and this system has a temperature of about 4,000 degrees. So the star is very cool, but that's not the only thing. The sun is an evolved star, is a mature system with about an estimated age of 5 billion years. But this other system, EUMIC has an age of about 20 million years. So it's much younger than the sun. When the sun was at the same age, the sun was very, very young. We don't even know if the planets were formed at that time. So now with EUMIC, we know that planets can form at that very young age of 20 million years old. So that's one thing we learned about the system. And we detect the second planet of this. And the first one was detected in I think 2019 or 2020. And then the second we detected in 2020 as well. So this, but now there is a hint of at least four planets in this system. So it's a multi-planet system with several planets around the cool dwarf, very close to us and very young. So all of these make this very interesting for this system because no other system is like this. No other system is that close to us, that young, and with so many planets. So it is very special. That's I think why this is you call attention, and many people like this a lot.
Okay, perfect. I'm Narusha. I don't know. Do you have any questions?
I think a bit more of like a technical one. Like you mentioned that you used different telescopes within your PhD research and now as well. Are these telescopes in different wavelengths? And if they are in different wavelengths, so like a multi-wavelength study, what is the different characteristics or what is the differences in each telescope or wavelength? What are you trying to get from each one? Like what are the characteristics you're trying to get from the different wavelengths?
Okay. When we're dealing with different wavelengths, well, in the case of my research, when I mean different wavelengths or different spectral ranges, is not that very different in a sense, because you still use optical telescopes. You just use different detectors and different instrumentation to detect in slightly different ranges, but mainly in the optical and in the near infrared. So that's the two main wavelengths that I use in my research. Of course, you could still go do astronomy in the radial. You could still do astronomy in the X-ray and gamma rays. Are very far from those, so very different also in the way you detect it. So when I talk in different wavelengths, it's different, but not that much in a sense. But still, you can learn different things from different wavelengths ranges. in the optical mainly, you were detecting hot stars because the emission of those stars peaks in the range of the optical, like our sun. You know, our eyes are evolved, or they evolved over time, you know, biologically to detect the light from the sun. So we basically have eyes that are more suitable to the optical range, and we don't see in infrared light, right? But our telescopes do. So we can still learn things in an infrared. And what's mainly we can learn is when you get cooler stars, they don't peak in the optical, they peak in the near infrared. So for cooler stars like Eumic, it's much better to observe it in the infrared. So that's one difference. Another difference is the energy of atoms when they emit light. Mainly they are in the optical, but when you get to molecules, that's the atoms together, you know, like water is a molecule, carbon dioxide, etc. They have absorption in the near infrared. So if you want to detect atoms, you go to optical. If you want to detect molecules, you go to near infrared. Or depending on the molecule, you could go in different ranges in the near infrared, and depending on the atom, you could go in different ranges in the optical as well. So if you want to learn specific composition of some planets or some stars, you have to go to different wavelength ranges. So that's mainly what makes us to go to different ranges of wavelengths. But there's another thing, you know, sometimes it's not only the wavelengths that matters, it matters the technique you use. As I mentioned, we detect the planets using photometry from space telescopes, but then after that you have to follow up, and you have to do spectroscopy or do astrometry or interferometry or different techniques to learn more about those systems. So that's how it works.
Okay, that's really cool. You mentioned some things about the different instruments that you've worked for and the software and things like that. So I have two questions. So how did the environments where the instrument itself affect the detection of exoplanets? Since exoplanets is a bit more difficult to detect since it gives you like maybe one spike or like periodically. So how did the environment affect those instruments or the detections rather? And then also, I know that some instruments or telescopes have automated software that refines the data. How does those software deal with those detections? Like, does it kick it out, or is it tuned finally in order to detect those exoplanets?
Mm-hmm. Okay, so you are absolutely right. The environment, they affect a lot the instrumentation, which is the you know, that's the challenge the scientists has when to develop instrumentation capable of detecting exoplanets, because exoplanets they are small bodies around big stars, and they're very faint around very bright stars. So all of that difference between these two bodies, and they're so close together and very far away from us, makes it very hard to detect those that small body. So even you know, whether you're trying to detect it in directly, taking pictures of the planet, or indirectly, this is all difficult. But so we have to develop technologies to overcome those difficulties. So some way you have to learn how or make your environment very well controlled in a way that you know all the potential problems or interference on your experiment to be able to detect those very tiny signals. So how do we do that? You know, how it's done. For example, this is one example in spectroscopy. spectroscopy, we've been doing this for a long time, but high resolution spectroscopy is more recent, because that's when the instrumentation developed to the point where you can make very high resolution to see separated lines in the spectra. But then your spectrograph is varying in because of the thermal variation during the night or during observations, makes dilatation and contraction of the instruments to change the way your spectra is recorded. So how do you do to control it? So you make basically an installation, or put your spectrograph inside of a fridge that is very well controlled in temperature, and you take the air out of this enclosure to make a vacuum inside, so the air won't transfer heat and won't vibrate and won't affect your measurements. And there are several other things you do to control it. So once you have everything controlled, you can start measuring things very tiny signals. So that's how you do that. But how the software handles or enter this the display, the software is actually when sometimes you already have the information to calibrate your instrument, but you're not using that information just because the software that you're using is not taking that information into account when you are doing your measurement. So if you develop a new software that takes that information into account, you may have a way to calibrate your data or to control things better to make that measurement of a tiny signal. So that's basically how things play out. Of course, this was just one example, but there are several different examples and different techniques and different methods. I hope that answered your question.
Yeah, it does. It does. And then more of a out there kind of question is, so you've been working with exoplanets for a while now, and how are we any closer to finding a exoplanet that's habitable? And like, are you able to detect those features or those characteristics on exoplanets itself? And how do you think that would affect us as humans and the universe and science in general?
Okay. Yeah, I think we're getting there. We're getting there, and we're in the right path. That's what I think. But of course, it's a recent field of research. So we're still learning things, we're still evolving. Our wish is, I think, if you put one of the big questions of astronomy is there life out there? Is there intelligent life out there? Is there planets in other systems that can host and develop life as Earth did on the solar system? So those are very valid questions. Those are scientific questions that are trying to be answered, but not directly. They are trying to be answered at some point when we reach the point where we can actually, detect planets in a very solid way and detect characteristics of planets to say, okay, this planet is habitable, this planet has life, and this planet has intelligent life, or so. But how far we are from that? I think we're not too far, but there are things being developed at the moment to get to that point. Our main limitations today, I think, is, well, first, our techniques, they are more sensitive to large planets, and very large planets, they are not the most suitable for life, because they are not for life as we know it. If we think of life on Earth, the only one example of life we know of, this big planets, they're not suitable, because the composition, the temperature, pressure, the distance they are from their host stars, and so on. So there are several characteristics that are not very good for life as we know it. But as we develop more and more instrumentation now, we are detecting a lot of planets in the habitable zone. What's the habitable zone? The habitable zone is defined as the region around the star where the temperature of the planet, due to the heat received from the star, the radiation from the star hits the planet, and the temperature of that planet is suitable to have liquid water on the surface. That means around between 0 and 100 degrees Celsius, something like that. But of course, there are several other things to consider. If you have an atmosphere, you can have greenhouse effect. If you have different compositions, you may have different heat capacity of the material there. So a lot of things can also interfere on that. So it's very much more complex than what I just described, but that's the basics of it. But we are detecting a lot of planets in the habitable zone of stars and small planets. So as I said, our techniques are more sensitive to large planets. Now we are detecting smaller and smaller planets reaching to the size of Earth around the regions not so close to the star, but more and more further from the star, to the point where it's in the habitable zone. But those are still just a few planets, and we just know they exist. We don't know much more about it because if they're harder to detect, they're even harder to follow up, to learn more. Like if you want to measure the composition of a hot Jupiter, that's okay. We have techniques for that now. We do transit spectroscopy. We can measure the composition of an atmosphere of that giant planet. But to measure the composition of the atmosphere of a small planet like the Earth and the habitable zone, that's a different problem, and we're still not there. We're not able with our instrumentation. But as I said, there are instrumentation being developed in that direction, like the ELTs, which is the extremely large telescopes. The size, mirror size of the order of 10 meters we already have, but 30 meters, 40 meters. So those telescopes is the next generation of telescopes. They will be able to reach much closer to that point where we can detect and characterize Earth. And also very space telescope missions that are tuned to detect planets. There are some missions that they're not only to detect, but to characterize also the planets. So they developed the instrumentation, the technology, just to tune to this kind of work, and then you can reach much more deeper on the characterization of these small planets. So I think that's where we're standing. Of course, everyone wants to know it. It's a it's a $1 million question, but it's indeed it's science. You want to reach to a point, so you have to work a lot and develop techniques, theory. You have to develop instrumentation and all that technology to reach to answer that.
Yes, definitely. That's definitely one of the questions I guess every human has whenever they hear someone's an astronomer or studying some sort of science. That being said, if you were to meet any person that has very little astronomy background, what would you describe your research as, like let's say in layman's terms, but in the most basic way? And how would you make it interesting for someone who might want to become an astronomer or specifically study exoplanets? How would you explain this to them and what it actually entails? Because a lot of people just think that it's looking up into the sky. So how would you explain that?
Yeah, it's exciting. Well, at least for me, it's exciting in many ways. Not only, of course, we all have that. Look at the sky and be amazed by, you know, the universe. You're looking at the unknown and things that you want to, you're curious about. But science has, you know, like in my career, I found out that there are many things you learn that are worth it. And not only to just look at the sky and wonder it, but when you start developing some specific scientific experiment, for example, and then you see the results coming out of it, and you see that you are actually adding something new to the textbooks, that is very rewarding, I think. And besides, you know, that happens with every scientist. You know, you're learning about something very specific. You're trying to reach something very specific, but you have to know many other areas to do that. Sometimes you have to know, you have to deal with even areas that you don't even think about. I'm not talking about physics, mathematics, and about. Sometimes you have to do the right relationship with people. Sometimes you have to do bureaucracy, write text, proposals, interact with people, learn other languages. So all of that is knowledge that's accumulated to make you reach that point. And that's, I think, is very rewarding, because those are things you use for life. You know, you don't use just for the science. So I think that's a big motivation, I would tell to people. But of course, you know, some scientists, they work on medicine, some scientists, they work on chemistry or geology, different topics. So our main subject is astronomy. So we have to keep the focus on what you're doing, because if you don't, you just don't do things in a way, you don't reach out the point where you can actually find something new, because, you know, a lot of people are working on those things. So you have to focus on your work, but at the same time, I think it's very rewarding, because you have to deal or learn things from different areas. I don't know. That's, I think, the main message that I would say.
Thanks so much. I don't have any other questions.
Well, I had a couple of questions that were you lightly touched on them here and there, right? During your answering of your questions, right? But maybe just to go back in terms of telescopes and instrumentation, right? I think you mentioned that there are kind of limitations in terms of the environment, right, on Earth, right? If we were to send a telescope anywhere in space, right, where would you send it, and why that particular region in space?
Okay. Yeah. The space is not the same environment as Earth, but it also has its own environment that's also harmful for the instrumentation. So that's one thing. And the other problem of space, of course, it's much more expensive, because, you know, you have to put much more money to build an instrument to go to space. But besides, it's much more risky. So you have to be very careful. And you can't. Oh, sometimes you can. You know, like the Hubble telescope, when they sent the first time, they took the first image. The optics wasn't so good, so there was an optical issue. They had to send out a mission to change some, or to actually put an optical part that will fix that problem. So that was possible for Hubble, but for example, for James Webb, it's not possible. It's in a so far away orbit that no human space mission can go and come back easily to do that repair. So it has to work. And then, and you asked me where to put your telescope. I think the place really depends on what you're doing. You know, if you're doing, for example, surveys, large surveys or all sky surveys, like tests, you need to count for the sun, because the sun is on the way. So you have to look at parts of the sky where you're not pointing to the sun, you are not pointing to the Earth, because Earth is also a very bright object from this. If you're looking from this space telescopes, like the moon as well. So you got to count for all of that. And so your service will have to be in a place in space where you can look at places in a different direction of the sun, the Earth. And you have to make sure that this survey strategy that won't interfere in your science. If you have to continuously look at the specific object during all year long, that's one requirement. But if you can be pointing at that particular region of the sky for 30 days and then go to another one and then go back to that one, so this is a different strategy. And that's also a different place in space would benefit those surveys in a way or another. Like, for instance, James Webb is in the L2 orbit because it's a stable orbit, so it's an orbit that is following Earth. So you keep communication with the satellite very the same pace over all the year long. But it's far enough that you can look at the deep sky without interference of the Earth and the Sun. It's always looking back. So it's a very strategic place. Sometimes people mention putting a telescope on the moon. It's a good place to put a telescope on. The problem is it's very hard to go there and do any maintenance, or we don't know the stability of the ground of the moon as well. You have to deal with the brightness of the moon and etc. So for some things, it might be a good idea. For some other things, might not be as good. So it depends. But if you ask me where I would like to put a telescope, I think anywhere in space, depending, for example, if you, I remember when I was a student, I was asking myself why people don't put a very small telescope in space, because a small telescope in space would do much better than a big telescope on Earth, because the atmosphere interferes so much with our observations. And actually, many other missions later on actually use that idea using small telescopes, like TESS, for instance, is a 10-centimeter telescope. It's very small, but it does a lot of planet detection, so it makes a lot of sense. So yeah.
I guess that's all of the questions that I had on my end. I don't know if Narusha has any question. I think I have one last question, but I wanted to save it as the last question. I don't know, Narusha, do you still have any other questions?
No, I'm good. I'm good. I think I've asked all the questions and learned so much about exoplanets and how they're detected.
100%, 100%. Dr. Eder, I think my last question to you would be, what is your favorite song, or maybe what is the last song that you listened to? Outside of the
Favorite
science.
song?
Yeah, outside of the science.
Okay.
Yeah.
Oh, it's a difficult question because I have many songs I like. It changed
Yeah.
also. It depends. It really depends on my mood. Sometimes I like very chill songs. Sometimes I like more,
Yeah.
but I think I'm a very I can't say any specific one because I like so many songs.
Maybe you can give us
It's a
at least
hard question.
top three or top four that we could use. I mean, we must prepare to come to Brazil, right? In September, right?
Okay.
Yeah.
So Brazilian songs. Oh, difficult question. I didn't prepare for that.
This is just on a lighter note.
uh,
Nothing too hectic, right?
uh-huh.
Yeah.
No, I don't know. I just not thinking of any particular song at the moment. I don't know.
Do you
Well,
have
I
a
could
last song that you
say,
listen to?
sorry,
I'm saying, or do you have a maybe you can give us the last song that you listen to?
the last song that I listened to, I have to ask Alexa.
Uh,
I don't know. I don't know. It's a hard question. I can't
yeah.
come up with any song right now. But if you want, I can write you later
Okay, no, that's fine.
something like that.
That's fine. And then maybe just to close it off then I mean where's your favorite place on Earth? It is I mean like a tourist destination or what part what place would you love to visit?
If money was no option, if you could choose a place to be right now,
Yeah.
just to relax, not specifically scientifically, just like for fun,
Uh-huh.
where would you
For
be?
fun. Oh yeah, well, I enjoy places well around the ocean. I really enjoy that. I'm not too far from ocean, but I don't go that as often as I wish. So when I was living in Hawaii, actually, it was very nice because I could go to the ocean very often. So any place warm enough that you can actually go into the ocean. So let's exclude subtropical or
Yeah.
Yeah.
but I've been to some places that I would like to go back, that are very interesting and some, like places like here in South America, in the Andes, it's amazing. Patagonia is an amazing, beautiful land. I don't know Africa. I wish I could go because I've seen so many nice and beautiful places there as well on TV, and I wish I could go and visit. Um, and I don't know, some remote places would be very interesting too, not for very long, but like Antarctica or the Arctic, something like that. I think that would be very interesting. Only interesting, maybe not so pleased, but yeah.
Wonderful.
Anyway, but to spend more time, of course, for sure, I would like to be around the ocean, some I don't know, island, and I don't know, that would be some preference.
Yeah. And as an astronomer, do you often look up the sky at night and just marvel at what the sky has? I've seen with most astronomers, they often don't look, but they often look through telescopes, but then not with their naked eye. Do you take some time and look at the sky at night?
Oh, yeah, for sure. We never lose that. We just lose our time. We don't have
Yeah.
enough time when we start getting engaged in so many activities, but um, even not having as much time as I wish to do that, I still enjoy it when I have the chance to. Especially every time when we're at the observatory, I always take some time to go out and look at the sky and stare at that. I think that's the basic instinct that makes us do the science. So if you lose that, like, we're not
Yeah.
doing it for nothing.
Yeah. Yeah. No, 100%, 100%. No, and I think that is all from our side, Dr. Eder, and we'd really love to appreciate you for your time and for sharing your research with us. I hope this is not the last time we have an interview like this. We're hoping to engage with you more moving forward and building onto this relationship. I guess we're also working on. I think Brazil is hosting the presidency this year, and we're looking forward to going to Parachi, right? I think we were speaking to Bruno, and they were telling us they're booking us into Parachi, and we looked it up. It's one of I think it's a tourist. It's your perfect tourist destination, and it looks really wonderful from the pictures. And we are looking forward to meeting you and engaging with you further. Yeah,
Yeah, thank you, and thank you for inviting me to have the chance to give this interview for you and for the BRICS Astronomy, which I think it's an excellent initiative of uh, joining communities that are so similar in a way, because developing countries are very hard we talk about environment a little bit of instrumentation, but in the environment for astronomers to develop science is also a key to
Yeah.
to make good science, to make good detections, and to contribute to the textbook, as I said. So if we don't have the right environment, it's much more difficult to do that. But we're still doing it in all the BRICS countries. So I think it's amazing, and I appreciate you are doing this, and thank you very much.
No, thank you so
Thanks so
much.
much. Hopefully you can come visit us in South Africa soon. That would be
Yeah.
great.
I hope so. I really hope so.
Yeah, we have
Thank
very
you.
cold what you call this oceans in Asia. I doubt you'd want to go into the water.
Yeah. Where are you at?
So we are both based in Cape Town in South
Cape
Africa.
Town.
Yes.
Yep.
Okay, Cape Town is in very bottom, and there is an ocean. Nice.
Yeah. No, you should definitely come visit us sometime.
Yeah, definitely. Whenever I have a chance, I'll definitely do that.
Okay, perfect. Thank you so
Thank you
much.
for your time.
Thank you. Bye-bye.
Bye. What an incredible conversation we've had with our speaker. I hope you found that as insightful and as inspiring as I did. Thank you for tuning in with us. I hope you enjoyed this episode. Don't forget to like, share, and subscribe so you never miss out on amazing guests that we have on the show. I'd love to hear your thoughts. Drop a comment below and let us know what your favorite takeaway is from today's discussion. Until next time, stay curious and we'll see you on the next episode.